What you see on the screen are 5 of the parent functions that we've learned so far this year. What do they all have in common, class? 0, 0, and 1, 1. They all go through those 2 points, but after they pass those points, they differ. Some of them stay linear, some of them are curved, some of them have symmetry, some of them do not. Actually, the only one without symmetry would be the blue one, square root. All right, the rest of them all do. Today, we look at 2 new parent functions, and we hope to recognize their shapes when we see them. Say, oh, that's this, or that's that. There are 2 that we're going to learn, and we're going to learn a couple of key points that are on them. And here's one of them, y equals log x. At this point, you can start writing on the red graph paper if you haven't done so yet. Okay, continue your notes on the red graph paper. And before we graph log x in the first grid, let's graph its inverse, 10 to the x. These 2 functions are inverses of each other. And if you remember our lesson from 5.5 with inverses, that meant that their x and y coordinates were opposite or flipped. I like to use the word opposite because then we think negative, positive. They're flipped. They are interchanged. So if the point 2, 8 was on the function, what would be on its inverse? 8, 2. That particular point is not on either of these. So let's go ahead and graph the blue one by making a little table of values, and you can put this on the first grid on your red graph paper. Like any good function, we should probably start exploring it when x equals 0. That will give us a very important part of the graph known as its blank, blank. Blank, blank, blank-intercept. Y-intercept, yeah. We're going to go ahead and find the y-intercept by plugging in 0. What's 10 to the 0? 1. Anything to the 0 is 1. So if you remember from the parent functions on this screen, they all went through 0, 0, and 1, 1. This parent function goes through 0, 1. It's horrible. All right. I'm going to darken in my x and y axis. Okay. So there we have 0, 1 as the y-intercept of this blue parent function. Go ahead and plot it. And then let's explore more and see what happens when you plug in 1. 10 to the 1. Anything to the 1 is itself. So 10 to the 1 is 10. So this function, this parent function, 10 to the x, goes from 0, 1 way up to 1, 10. That's the next key point on it. So would you say it's rising pretty rapidly? Especially when you plug in 2. If you plug in 2, it would be 10 squared, and 10 squared is 100. So yeah, it's way off your graph already. 3 would be 1,000, 4 would be 10,000. By the time you get to 9, you're not even off the grid to the right. It would be up to 1 billion. Okay? So it's rising pretty rapidly. So here's how we'll indicate that. Connect these with an arrow. It goes up fast. As fast as it's going upward to the right, that's pretty much the rate at which it slows down as you go to the left. It's going to come to a screeching halt when you get to the other side of the y-axis. Imagine one of those slides at a water park, the really tall ones, right? Where you go down, yep, you go down really fast, it's really steep, and then at the end it's just like, that's what this does, right? That's what this graph will do. It's going to come way down real fast, and then it's going to level off completely, and here's why. What happens when we enter in our table of values some negative numbers? I'm going to make a different table so I don't have to keep extending the page. If I put in -1, you don't get an error. You can do 10 to the -1. What do you get? 0.1, 1/10. It's pretty small. It's a tenth of a block. Small. Put in -2. Too many zeros. 0.01, that's 1/100th. It's 1/100th of a block. That's like if one of those little red blocks could be broken up into 100 pieces, you would only be looking at one of them, right? 1/100th. -3, you're already at what? 0.001. So that's why when we graph to the left, you just kind of say, yeah, it's getting really, really close to that axis. It's approaching what we called a couple of units ago a limit. The limit is 0. It never crosses 0. It's a smooth curve. It doesn't reach a point. It kind of, right here, it's curvy. But it levels off. It never gets completely horizontal. It's one of those brain-hurting moments where how can something be dropping but at the same time be leveling off? Well, it does. It continues to get closer and closer to that axis without bound. It never curls back up. It always goes downward but never crosses 0. That's the graph of 10 to the x. Do you remember in this case what we called the x-axis? A line that the graph is getting close to but never crossing. Its first syllable sounds like a swear word. Starts with an A. S. Y. M. P. Sounds like I'm just saying letters, huh? It's called an asymptote. I thought we've talked about it. A tote, like a tote bag that they give away at the Penguin game. Yes, it's called an asymptote, and that is a horizontal or vertical or slanted line that a graph is getting close to without crossing. That's called an asymptote. If you prefer, you could call it an asymptote. Okay? It's a horizontal, vertical, or slanted line, so any line. A line that the graph approaches but never crosses. It is singular asymptote. So here, the line y = 0 would be the asymptote of the graph. It would never cross that line. Everything that we see on the screen right now, then, is the graph of y = 10 to the x, and it's in blue. From here on out, the graph will focus on y = log x. Now, one thing to remember, when you're graphing y = log x, what's understood to be right here? 10. A 10. All right? So if you think about the definition of a log, it was 10 to the y equals x. Well, what does this say? 10 to the equals, you see how the x and y switched places? Listen again. 10 to the y equals x versus 10 to the x equals y. The x and y switched places, making them inverses of each other. Okay? All right, I'm just going to get rid of some of that purple stuff there, and we're going to go and do the log function. So let's make a table of values. I'm going to get rid of this and just focus on log. So let's make a table of values with x and y. I wish I didn't erase all both tables, but you can tell them to me. What we need to do with our table of values from the blue one is flip them around. So one of the points on the blue graph was 0, 1. What's going to be its brother point on the red one? 0. You got it. Okay. The other key point on the blue graph was 1, 10. Flip it. So what we're saying here is, if I put in 1, what's the log of 1? 0. When you put in 1, right, it's saying 10 to the what is 1? 0. Okay? If you put a 10 here, 10 to the what is 10? 1. Okay? The next point on our blue graph would have been 2 comma 100. What would that be on the red? 100 comma 2. Let's just see if that makes sense when we think, what if I put 100 in here? 10 to the what is 100? 2. That's where these points are coming from. So let's plot those. I don't know if we'll be able to plot all three, but let's plot them by going to our graph and putting a point at 1 comma 0, 10 comma 1, and 100 comma 2. Oh, sorry. I would have to go out in the hall to graph that one, right? Yeah, almost hurt. Okay, so 100 comma 2 would be how far to the right? Just say real far to the right. Real far to the right. Be 100 units to the right. So while the blue graph was going up very rapidly, what's this one doing? Cross very rapidly. Now, on the flip side, while the blue graph came to a screeching halt and curved this way, right? This one's going to go, woo. While the blue graph got very, very close to the x-axis, the red graph is going to get very, very close to the y-axis. They're inverses. Everything is opposite. Okay? Well, let's do this. Do you remember when we made the second table of values for the blue one, and it involved negatives and decimals? Flip those 3 points around for me. The first one was negative 1.1. What will it be now? 0.1 comma negative 1. Then 0.01 comma negative 2. Then 0.001 negative 3. The x's and y's from the graph of 10 to the x all get flip-flopped for log x. They're inverses. So imagine where those points will be. 0.1 comma negative 1. Somewhere around there. 0.01, which is over just a tiny bit, comma negative 2. And 0.001 comma negative 3. To get down to negative 6, you'd be at 0.000001. Okay? To get down to negative 9, you'd be at 0.00000001. All right? So very, very tiny x values, very, very negative y values. So that's what the graph of y equals log x looks like. Its key points are, instead of 0, 1, what's this one? 1, 0. And instead of 1 comma 10, 10 comma 1. Instead of having an asymptote on the x-axis, this one's going to have the asymptote where? The y-axis. Okay? Instead of the limit being y equals 0, like it was in blue, this limit is x equals 0 in red. That's the x value that it's never crossing. And if you remember from yesterday, with our definition of a log, we said that when you have log of a base b, what did a and b have to be? Not the same. They couldn't be negative or 0, right? Okay. So the base here is what? In here, it's understood to be 10. So is that negative or 0? No. And we're finding the log of x. What part of the graph, watch this, what part of the graph is the red graph completely, why'd you do that? Completely ignoring and not touching? And the whole left side. What's x over here? Positive or negative? And it's avoiding it, right? The red graph is completely avoiding all the x's that are negative. Okay? Yeah, that was a mistake. Sorry about that. Touchy smartboard. All right. Last thing. Here we go. Significance of this line. I'm going to use blue. Let's use this. That's the line y equals x. Tilt your head to the right. I know we got a lot of colors going on there right now, but what's going on with the blue graph versus the red graph? They're symmetrical, right? The blue graph and the red graph are symmetrical. Therefore, they are inverses of each other. Okay?